All right, hi year 11s, this is Mr. Lim here again, and this is our first video on gases, the kinetic theory of gases. All right, so we're going to be learning about ideal gases and real gases. So let's get started. Okay, so here's first of all, let's start with a question. Which one has more kinetic energy, a solid at 25 degrees Celsius or a gas at 25 degrees Celsius? All right, so have a think. Let's go through the idea. The idea is that they should, in fact, have the same amount of energy, right? Why do they have the same amount of kinetic energy? It's because they're at the same temperature. So then why is one thing a solid and one thing a gas, right? So the idea is that those particles, they might be moving and vibrating with a certain amount of energy, but the attraction that they have towards each other can vary, right? Some substances might have a large attraction towards each other, and some will have only a very small attraction to each other. All right. So the ones that have a large attraction to each other will be a solid because they're not going to be able to break free from each other at that 25 degrees Celsius. Whereas a gas, or some other substances or gases, they have a low attraction towards each other. And so therefore, even at that amount of energy, they have the energy to move apart from each other, which is why we say that, with the different types of chemical bonding, your metallic, ionic, and covalent network all have very strong attractions between the particles, but covalent molecular substances generally have low amounts of energy between those particles, and therefore they are generally gaseous at lower temperatures, right? But you should recognize that they have the same amount of energy. It's just what's holding them together is at different levels, and therefore will affect what state they're in at that same temperature. Have the same energy, but the strength of attraction is different. Okay, so we all know that gases have some common properties, such as, well, hopefully from year 8, they can diffuse, they are compressible, which means that they can be pushed into smaller shapes or smaller spaces or smaller volumes and then expand to large volumes, so they have volume variability. They take the shape of their container and they exert a pressure on the container, which we'll go through in our next video. What is pressure? All right, but those are some common properties of gases. They share these common characteristics because they share common characteristics at the atomic or molecular level. All right, so these common properties or characteristics make up the kinetic theory of ideal gases. All right, so let's go through these. So number 1, gases are composed of very small particles. Okay, that's why you can see through them, because if they're made up of small particles, yet they take up a lot of space. We'll go through that in a bit. They move in rapid, random, linear motion, which means they move in straight lines quickly, but randomly, right? The size of the particle is negligible, which means that there has no real value compared to the space between the particles. So what does that mean? Here I have 2 small particles, right? And the space between them is effectively infinity compared to the space that they actually take up, right? So that space there and that space there is so small, it's negligible compared to the space in between them, which could be counted as infinity. All right, that idea that the size of the particles is negligible compared to the space between particles gives rise to the idea that some substances can be compressed. Right, so they can be compressed because there's all this empty space between the particles. Right, the fact that gases move in rapid, random, linear motion will effectively mean that they will diffuse and take the shape of their container as well. All right, gas particles collide with each other and with their container walls, which is kind of part of what it means to exert pressure, which we'll go through later on. All right, so they just collide with each other, and those collisions between particles is fully elastic, right? What does fully elastic mean? It means that the amount of energy that they begin with when they crash into each other is the same as the amount of energy they leave with, right? So maybe I have these 2 particles, here's one particle, here's another particle, this one might have 100 units of energy, this one might have 50 units of energy, right? They collide with each other, and then they bounce away. They bounce away from each other, right? And they might have 80 now because it's transferred some energy. How much energy would have been transferred? Like, well, 20 units. So this one will have gained 20 units. So the idea is that the kinetic energy before is equal to after. Okay, that's elastic collisions. Right, and then particles have a range of kinetic energies, and as the temperature increases, the average kinetic energy of the particles also increases. So this is what we dealt with a little bit before in intermolecular forces, but the idea is that you have a bell curve of particles, with this is, on this side is the number of particles, this side here is the kinetic energy, EK or KE, I don't know what, like whatever you feel like writing, but you have to recognize it's kinetic energy. Right, so these ones here have high, these ones here have low, but you'll recognize that because this crosses at the origin, no particles have zero energy, right? So they have a range of kinetic energies, and as the temperature increases, the average kinetic energy, which is the peak, increases as well, which means that it moves towards the right. So something that is hotter might look like this here, right? So that would be the idea that they have a range of kinetic energies. And then the final one is that they have negligible attraction between particles. Okay, so that effectively those particles don't attract each other, or the force of attraction is so close to zero that it doesn't have to be counted. All right, so those are the characteristics of a kinetic theory of ideal gases, right? You kind of have to know those 7 dot points there, right? However, these are the characteristics of ideal gases, but real gases do not have all of these characteristics. So the particles do not have negligible size. Their collisions are not elastic, or not fully elastic, and there is attraction between particles. Okay, so real gases don't have all of those characteristics. So the difference between the characteristics of real and ideal gases is generally very small at standard temperatures and pressures, or even high temperatures and low pressures, right? So ideal and real gases can be thought of as the same things under most conditions, but when they get squeezed, pushed together, or if they get cooled down, then their properties significantly change. Okay, so let's go through those ideas. So when compressed or cooled, the particles will be very close to each other, or nearer to each other, or interact with each other for longer periods of time. If you think about it, two things that are moving very slowly and they collide with each other, their interactions will be greater than two things that are moving fast and then bounce off each other, because the slower things will bounce off each other slowly and therefore spend more time interacting with each other because they'll be close to each other for more time. All right, but the idea is that when they're compressed or cooled, at some point they will liquefy or solidify depending on what the type of gas is, and thus the particles will have size. The idea is that they have like when you bring them close together, they will actually take up some space, and so therefore their size is not negligible to the gaps between them. All right, and so when you get to like highly compressed gases, they don't have that kind of relationship. All right, so different gases at the same temperature can have the same kinetic energies, right? So that's what we dealt with before. However, because they're made up of particles of different masses, right, they will have different velocities, because the kinetic energy is the product of both mass and velocity, and thus different gases will diffuse at different rates due to the speed at which the particles can move. Okay, so some ideas here is that, okay, if I have a O2 versus N2, okay, so O2 has a molar mass of 16. No, wait, 32, right? And N2 has a molar mass of 28, right? So if this is their molar mass, O2 is a bigger molecule. If they have the same EK, right? So if EK is equal, say they have 100 units each, right? That means that this one, the smaller particle, the N2, with the same amount of kinetic energy, right? They have to be moving faster compared to the O2, which will be moving slower because it has a larger mass, right? But the kinetic energy is EK is equal to half mv squared, right? So it's mass times velocity. So because you have a bigger mass, you have to have a smaller velocity. Like if you're talking about O2 compared to N2. All right, so they will move at different speeds, right, and diffuse at different rates. And because they have different sizes, they'll also, well, actually, when you compress them, they'll have size, but also those different sizes do make a difference to their speeds as well. All right, and then finally, the other bits of information. So the collisions between particles and between their surroundings are not completely elastic, meaning that energy can be transferred from the surroundings based on their relative temperatures. So the idea there is that if I have a container, right, and outside the container is hot and inside the container is cold, right, you should work out that, heat energy will be transferred into the thing, right? So the particles that are inside here, when they collide with a wall, they're going to bounce off, right? And then as they collide with that wall, they might have low energy. And then when they bounce back, they'll have slightly higher energy. It's not that they're going to have high energy, but they're going to have slightly higher energy because they're going to have transferred a little bit of energy from the containers to container wall to the particle, and therefore be moving slightly faster. And so eventually the cold gas inside will reach same temperature as the hot outside. All right. Also, the idea is that when two particles collide with each other, right, they will bounce back with slightly less energy because there's attraction between those two substances. All right, and that comes to our last point here. There is attraction between particles, that if you reduce the kinetic energy of a gas enough, the forces of attraction will keep the particles together and substance will liquefy, right? Which is what we talked about at the very beginning, that the kinetic energy of a substance is only one part of why it's a solid, liquid, or gas, or like, the melting and boiling point of it, right? The other idea is that the amount of attraction between the particles, right, determines whether it'll be a solid, liquid, or gas. And so gases generally have low intermolecular forces, but they don't have no intermolecular forces. And so that attraction there, if you reduce the speed of the particles enough, you will eventually have those particles stick together and turn into a liquid or a gas or a solid, depending on what the substance is, and therefore there is attraction between those particles. All right, and that's the differences between real and ideal gases, and we'll be going through a couple of ideas in the next couple of videos. Adios.